Today, we're talking about the tiny, tiny materials that make our entire digital world go round. Semiconductors. Seriously, they're in everything.
So, let's start with a really fundamental question. We're pretty good at making electricity, getting it to flow from point A to point B. But how do you actually control it? How do you tell it what to do, when to do it, and how much to do?
For the longest time, we basically had two modes, on and off. On one hand, you've got conductors, like copper wire. They're the permanent go signal. Electricity just flows right through. And on the other hand, you've got insulators, like rubber, which are a permanent stop signal. Nothing gets through.
But here's the thing. Just having a simple on-off switch isn't enough to build something complex, like a computer. You need more than that. You need nuance. You don't just need a light switch. You need a dimmer switch.
And that need for something in between, something controllable, brings us right to the hero of today's story, the semiconductor.
And this chart really tells you everything you need to know. Just look at the resistivity, which is basically just a fancy word for how much a material fights the flow of electricity. Copper barely puts up a fight at all. Glass is like a brick wall. And then there's silicon, smack dab in the middle.
It lives in this perfect Goldilocks zone. It's not a great conductor, but it's not a great insulator either. And that's not a weakness, that is its superpower. That's what makes it so incredibly useful.
So what's the secret? What gives semiconductors this magical middle ground property? Well, for that, we've got to zoom way, way in, all the way down to the atomic level.
You see, unlike a metal where electrons are just zipping around all over the place, a silicon crystal is super orderly. Every single silicon atom shares its outer electrons with its neighbors, forming this really stable, strong crystal structure. They're all holding hands in what we call covalent bonds.
And when we have a semiconductor that's perfectly pure, with a perfect crystal structure like this, it gets a special name. We call it an intrinsic semiconductor. Think of it as our blank canvas. Now, those bonds are strong, but they're not unbreakable. In fact, just a little bit of heat, even just the ambient energy at room temperature, can be enough to knock an electron loose. It breaks free from its spot, and when it does, it leaves behind an empty space, a hole.
And here is where things get really cool. That free electron, which has a negative charge, can obviously move around and carry a current. But get this, soak in the hole. When an electron from a nearby bond hops over to fill that empty spot, it leaves a new hole behind. So it looks like the positive hole is actually moving through the crystal. Both the electron and the hole can carry current.
So this pure intrinsic semiconductor is pretty neat, right? But on its own, it just doesn't conduct enough electricity to be all that useful. The real breakthrough, the thing that changed everything, was when scientists figured out how to tweak.
And they did it through a process called doping. This is where you intentionally introduce a tiny, tiny amount of a specific impurity into that pure silicon crystal. It's like adding a single drop of dye into a giant swimming pool, a tiny change that has a massive, massive impact.
And once we do that, our pure intrinsic semiconductor gets an upgrade. It becomes what we call an extrinsic semiconductor, one that has been custom-tailored to do exactly what we want it to do. So how does that work? How can adding a few different atoms change things so much? Well, by choosing what kind of impurity to add, we can create two totally different flavors of semiconductor. And these two flavors are the fundamental building blocks of, well, everything.
Okay, so for the first type, we're going to add an atom like arsenic. Now remember, our silicon atoms have 4 outer electrons to share. Arsenic is a bit of an overachiever. It has 5.
So, when you drop that arsenic atom into the silicon crystal, 4 of its electrons pair up nicely with the neighboring silicon atoms. But that leaves 1 electron left over. It's a free agent. It's not tied down in a bond, so it's free to move. The arsenic atom has effectively donated a free electron to the crystal. And what we get is an N-type semiconductor. N is for negative, which is easy to remember because we've just flooded the material with extra negative charge carriers, these free electrons. They become the majority carriers, making the material much more conductive.
All right, so for our second flavor, we do the complete opposite. This time we'll add an impurity like indium. And indium atoms only have 3 outer electrons.
So when an indium atom takes a spot in the crystal, it tries its best, but it can only form 3 bonds. That leaves an incomplete bond. It creates one of those holes we talked about. It's an empty spot that is just waiting to accept an electron.
This process creates a p-type semiconductor. P is for positive, because we've just created a whole bunch of these positive charge carriers, the holes. In this material, the holes are now the majority carriers.
So let's just recap.
Because this is the whole game right here. We started with one pure material, silicon, and by cleverly doping it, we've engineered it into two new, powerful materials. One with a bunch of extra electrons, the N-type, and another with a bunch of extra empty seats, the P-type.
Which leads us to the single most important question in the history of modern technology. The question that is the foundation of every transistor, every microchip, and every computer on the planet. What happens when you bring them together?